Hi, physics students. Today we are going to go over some class notes and then you'll have some time to work on some practice problems. Let's start with our warm-up this morning. So you'll see that there is this graph of an oscillating spring. And what you're going to do is determine the period and frequency of the wave and then how far does it travel and then what is the displacement. So pause this video and do this on your own. All right, so let's go over this problem. So remember to find the period. This is the full rotation, so up and down of an object. So this means that my period, big T, is equal to 4 seconds, and my frequency is 1 over my period, so that's 1/4 hertz, or 1 over seconds. For my displacement, I'm going up 0.5, down 0.5, down again, and then back up. So my distance would equal 2 meters, and my displacement would equal 0 meters because my start and stop is at the same time. The big focus of today is talking about what is the energy in a spring. So we're going to start off with vertical springs. So we're going to talk about 3 different types of energy. First, our gravitational potential energy, which we've talked about a lot, kinetic energy, and then finally spring potential energy, which we kind of talked about in energy, but I told you that it would come back later. So as a reminder for my spring potential energy equation, K is our spring constant, and I can find that using Hooke's law, and my X is the amount of stretch. Okay, so let's look through this situation. We have a spring. It is starting at a neutral spot, and then it is released. So at this height here, I'm going to have my max UG. I'm going to have no KE and no spring potential energy. Why? Because it is not extended at all. It's in a neutral position. So this means my total energy is equal to mgh at the top, my potential energy. Now we're going to look at halfway through when we're at this equilibrium part. So at this point, I still have gravitational potential energy. Now I'm going to have spring energy because it's stretched, and then I also have kinetic energy. So if I write this out, this is going to say my total energy equals my gravitational potential energy, my spring potential energy, and finally my kinetic energy. I'm just going to put this as total, and then I can plug in my numbers. Now, this situation, I might want to solve for something. Typically we solve for velocity, lots of different things. Now, if I actually plug in my variables, which I think is really important to note here, I'd have mgh minus x1 plus 1/2 k x1 squared plus 1/2 mv squared. And lastly, when this thing is all the way at the bottom, it is stretched completely, there's no height, and before it goes back up, it's at rest. So I have no Ke or gravitational potential energy, but I have max spring potential energy. So for my equation, total equals 1/2 K x2 squared. And like I said, from here we have a lot of different things that I could solve for. Let's look at another example. Now remember that we start with the spring not stretched. Sometimes students kind of get confused and we think, okay, I put in my mass and then it starts stretching, which is totally true, but the moment it's put on, it is not stretched at all. So if I think about this, if this goes down in a total amount of T and then back all the way up, that means my period would be equal to 2T. And then my frequency is 1 over 2T. why I like to show this diagram is that it shows that my equilibrium does not necessarily have to equal 0. Because we're talking about energy here, we can see that D is the total stretch from the start to the end. So graphing this one would actually look a little bit different. We're not going to do an example, but it is something like that I like to bring out, that my equilibrium doesn't necessarily have to equal 0. Now let's look at horizontal. When I look at a horizontal spring, it is only moving in the horizontal direction. Therefore, I have no gravitational potential energy. In a horizontal situation, I have to compress or stretch a string to get it started. So in this example, this spring is pulled, so in number 1, all the way to the right for an amplitude of A. At this point, I have a max spring potential energy. When it's released and I go through my equilibrium, I have my max KE, and then it compresses all the way, and once again, I have max spring potential energy. And then this repeats. So when I look at equations for this, it is a little bit easier to determine based off of just my stretch and then my velocity. So I could determine my total energy at the beginning if I take my 1/2 kx squared. At the max ke part, this would equal 1/2 mv squared equals my total energy. Now, I like to point out in this one, this is a little bit easier to conceptualize what the graph would look like. I'm going to start with my amplitude, which is A. And then I have my time. So let's say to travel to equilibrium, I have a time in each of these sections. 2t, 3t, and 4t. So this graph is starting at A, coming through equilibrium, and then down to the bottom, and then it comes back up. So that's one full period. I'll write in that this is point 1, point 2, 3, 4, and 5. Make sure you've taken your notes. Now you need to work on 13.1, 1, 2, 6, and then 13.2, 8, 9, 12, 15, 18, and that's on book page 445. To complete the assignment for today, you're going to work on those problems, check your answers on those odd problems, and then upload a picture. We'll go over it next block.